Hi everybody, my name is Dimitris Koutsoukos and I'm going to present you NVM. Is it not very meaningful for databases? This is joint work with Raghav Bhartia, Michal Friedman, Anna Klimovic, and Gustavo Alonso. I'm sure you are all very familiar with the CPU memory performance gap or memory wall. To summarize it, CPUs are becoming increasingly faster in a rate that is disproportionate to main memory. This leads to a significant bottleneck where the CPU often spends time waiting for data from the slower memory, thereby hindering the overall performance of the computing system. The CPU memory performance gap is being exacerbated by modern computing trends. As we generate and use more data, and the workloads are becoming more and more demanding and time sensitive, the pressure on the memory subsystem grows, making the processor memory performance gap an even more critical challenge. To this end, a number of solutions has been proposed. To start, we can have software optimizations such as data pruning or more efficient memory algorithms. We can also scale our systems, making them distributed with techniques like data sharding or compute storage disaggregation, like Amazon does for S3, for example. Lastly, several advanced memory technologies have been developed, from far or remote memory to high bandwidth memory and non-volatile or persistent memory. The last one will be the main topic of the presentation today. I'm going to use the terms NVM and PMEM interchangeably for the rest of the presentation. As mentioned, non-volatile memory has been proposed as a solution to alleviate the memory pressure and accelerate I/O. PMEM is both cheaper and has a higher capacity than DRAM. It is byte addressable and it persists data. This comes at the price of higher latency and lower bandwidth. It also became commercially available from Intel in 2019 in the form of Intel Optane persistent memory. Although in general NVM has been extensively studied in the context of databases, the majority of these studies has been done before the commercial release of PMEM. However, DBMSs are complex systems with many knobs that behave very differently as workloads and input size vary. Existing studies give only a partial picture, providing only high-level conclusions, and are mostly based on micro or small-scale benchmarks. Furthermore, they do not explore how database knobs and other operations, for example, join types or query plans, affect PMEM's behavior. To this end, in this paper, we provide the first extensive analysis of database engines using Intel Optane persistent memory. We benchmarked 5 DBMSs, and namely PostgreSQL, MySQL, SQL Server, DuckDB, and VaultDB, and one key value store, namely the RocksDB, using OLAP and OLTP benchmarks, and more specifically TPC8, TPCC, and the Yahoo Cloud Streaming benchmark. We experimented with various knobs and altered a variety of database and workload configurations. Before we dive into our insights from this study, let's first cover some necessary background. PMEM operates in 3 modes: memory mode, UpDirect mode, and mixed mode. In memory mode, PMEM acts as volatile memory, while DRAM serves as an L4 direct map cache. The integrated memory controller manages data traffic between DRAM and PMEM, with applications experiencing DRAM latency for cache hits and both PMEM and DRAM latency for cache misses. Applications do not need any source code changes to use this mode. In UpDirect mode, PMEM serves as persistent storage, offering strict read-write operations in interleaved or standalone regions. There are a number of configurable namespaces, but Intel recommends FSDAX for DAX-aware file systems. FSDAX eliminates the OS page cache in the I/O path, allowing mmap to directly map to persistent memory media. Finally, mixed mode combines memory and UpDirect modes using DRAM as an L4 cache. Users can configure the memory percentage for volatile memory or disk usage, but Intel suggests a minimum of 1:4 ratio DRAM to PMEM for cost efficiency. And now that we have gotten the necessary information, let's dive directly into the most important insights from our study. For each insight, I am going to give a few examples of where we noticed. Our first insight is that memory mode does not offer a significant performance advantage. For all the engines and benchmarks, in the vast majority of cases, memory mode with its larger volatile memory capacity does not offer any performance advantage. There are even cases where performance is slightly worse. The only case where memory mode is useful is for queries with sequential accesses and low number of reads-writes to memory. That happens because the DBMS can take advantage of the larger OS page cache offered by the larger volatile memory capacity, and together with prefetching, these queries can have a small speedup compared to configurations that do not use PMM at all. You can see this insight in the following graph that shows the runtime of TPC-8 scale factor 100 for Postgres. For the majority of queries, the running time is the same or worse as the default mode, and by default mode, we mean a system that doesn't use PMM at all. There are 3 queries that have a significant performance advantage, 9, 15, and 20. These queries not only have a larger working set than the DRAM L4 cache, but also need to have a working set larger than the OS page cache, and the improvements are due to the memory structure that the systems use to handle memory and how the DBMS utilizes the OS page cache. To understand where the overhead comes from, we saw the DRAM write bandwidth consumed by each query for the default and memory modes for PostgreSQL, although we observe similar results for the other database systems and the read bandwidth. For all the queries, we read and write more data from DRAM in memory mode compared to the default mode across databases. This happens due to the conflict cache misses in the DRAM L4 cache, which also causes additional memory traffic between PMM and DRAM, and also because during a DRAM write, the system has to read the dirty lines and flash them to PMM. These 2 factors make the performance of memory mode suboptimal. Our second insight is that in systems where resources are limited, PMM in UpDirect mode is not as efficient as we would expect. In general, PMM in UpDirect mode involves the CPU as no DMA is available. When there is a lot of resource contention, the hardware advantage of PMM is almost negligible, or there are even large performance regressions. We notice this behavior, for example, in the running time of TPC-8's scale factor 100 for MySQL. MySQL runs all up queries using only 1 core. Especially for CPU-intensive queries like 113 or 18 that we have complex aggregations or joins, and the OS page cache with DMA prefetching works effectively, we can see that the running time of the default and UpDirect modes is very close, despite PMM having a larger read and write bandwidth. Another example is shown here for running TPCC with 1,000 warehouses on SQL Server with a high number of virtual users. For 64 and 128 users, the contention is so high that the default mode can have a higher transaction rate than the UpDirect mode. As TPCC is a mixed workload that has both reads and writes, this brings us to our next insight, and more specifically, that PMM requires careful fine-tuning for write or mixed workloads. Other studies have also noticed that heavy write workloads and read-write interference decreases PMM's performance dramatically. One example was TPCC that we saw previously. You can see a second example here. For RocksDB, running the workload A of the Yahoo Cloud Streaming Benchmarks that has a 50-50% of reads and writes, for 48 threads, the UpDirect mode throughput drops less than the throughput of 16 threads. Lastly, we have noticed that the lower latency of PMM in UpDirect mode does not always translate to an advantage equal to the hardware characteristics. Our micro benchmarks reveal that PMM has 30 times lower latency than SSDs, and in some cases, over 10 times higher read and write bandwidth. However, this difference does not result in the expected runtime reduction, as the OO path is not fully optimized. In UpDirect mode with FSDAX, that is recommended by Intel, there is no OS page cache, and DMA is unavailable since PMM is managed by the integrated memory controller and not as a peripheral device. Consequently, CPU resources are spent on I/O in UpDirect mode, while in default mode, DMA and the OS space cache can cover part of the lower latency, especially in CPU-intensive, I/O-heavy queries or in cases involving secondary indexes with table data stored in the OS space cache. Here we saw examples of such CPU-intensive queries for PostgreSQL for DPCA's scale factor 100. Although the UpDirect mode is faster, it's definitely much less than the 10x that we observe in the micro benchmarks, although we see that all these queries read the line item table, which is around 85 gigabytes of data together with indexes. We observe the same behavior for DuckDB when the optimizer chooses CPU-heavy operations, for example, index joins or hash group bys, where the UpDirect mode is very close or has worse performance than the default mode, for example, in queries 2, 15, and 18. As some of you or most of you might know, in July 2022, Intel decided to discontinue the Optane series. However, there is still an imbalance between CPU and DRAM, which leads to a low DRAM utilization. DRAM is also an expensive computing part. Therefore, there is still a need for an intermediate storage tier between DRAM and SSDs. This gap can be filled with the Compute Express Link or CXL, which is a cache-coherent interface for connecting CPUs, memory, and accelerators. CXL-attached memory can increase the memory capacity of servers, offering a fast storage memory tier to place hot data that does not fit in DRAM. Several characteristics of PMEM are relative to CXL-attached memory, such as byte addressability and near DRAM performance with higher capacity and opportunities for high energy efficiency. Therefore, our study provides insights on what system functions, for example, prefetching, low CPU utilization, query optimization hints, are available in the database context to avoid performance regressions. We plan to investigate that as part of our future work. To conclude, we evaluated PMEM on various engines and popular benchmarks. As to main takeaways, memory mode does not offer a significant performance advantage, and in UpDirect mode, PMEM has lower latency, but the I/O path is not fully optimized. Our study sheds light on how to efficiently integrate PMEM into the memory hierarchy and how to tune relational and non-relational systems to get the best performance of each configuration, given the higher cost, both in terms of storage and CPU. Thank you very much for your time.